Today, we're going to do a review of the Markov decision process, which we looked at last week. And then we're going to enter the major topic of this course, which is machine learning. Okay. And we're going to start off by looking at one of the most popular machine learning techniques, which is artificial neural networks. And then after we are done with ANNs, we look at deep neural networks. And those are perhaps the most important topics of this course. And then we will look at other techniques which have been traditionally been used and are still used, such as SVMs and other techniques, which are the traditional, neural network, the traditional techniques used for machine learning. And we'll also get a chance to be able to compare how the deep learning techniques compare with the traditional techniques. Okay. So let's take a quick look at last week. We were speaking about the MDPs using car maintenance example. And then we looked at how to determine Q values under specific examples, such as the grid world that we looked at. And then we looked at how to determine the Q values in the grid world. And we looked at the simplest version of it, where you simply had this equation for the Q values, where it was dependent on the reward as well as a maximum Q value that would be achieved in the next state, assuming that you would be taking the optimum path subsequently. Okay. And then we looked at this example where we looked at the iterative calculations of Q values. And then we also started looking at what would happen if you had uncertain outcome. Okay, and we simply said that you could take the previous value of Q, which was based on the following equation, the reward plus the maximum value of Q in the next state. And if you have uncertainty, then all you do is simply put an expected value over here. Okay, so both of these would become probabilistic. And when you have an expected value over here, then all you have to do is take this value over here, which you're using. And when you're doing expectations, if you remember your intro to statistics, you simply add the probability of that event happening. Okay, so you simply add the probability of that event, and then you sum over all the possible values. Okay, so here you're summing over all the possible future subsequent states that could happen in t plus 1, given that you are in ST. Okay. So we looked at a particular example, and here we said that take this example where the probability of moving in the desired direction is 90%, very similar to what we've already seen before. And the probability of moving in the opposite direction, that there's only one opposite direction in this case, is 10%. Okay. So how would we calculate this? Well, we could use an iterative technique as we did in the past. So let's try this out. And again, I need your help over here. Can somebody tell me what this would be? So we're saying there's a 90% chance of moving in the desired direction and 10% chance of moving in the opposite direction. So here we're trying to calculate the Q value going in the upward direction from state S3, okay, which means that we're trying to go into state S4. So somebody help me out over here. Sorry? 0.9 is the probability of going in the upward direction. And so that's the probability. What's the reward of going in that direction? It's plus 1 minus a movement cost. All right. And then the maximum value of the Q value if you go into the next state, which is S4. Now we said that since S4 is a terminal state, the maximum value, there's not going to be any further Q value, so this is going to be 0. Is that it? Then you're going to add the probability of going in the opposite direction, which is 10%. So now we're going to go in the downward direction into S2. Okay. And what's the reward over there? What's the reward of going from S3 to S2? There's no reward in S2. There's only a movement cost. So it's going to be negative 0.1 over here. And what's the maximum value of the Q? The maximum value of the Q value, given that in the next stage you take the optimal decision, right? So what's the maximum value over here? Well, so far it's 0. Okay, so it's going to be 0. And so what is this going to come up to be? 0.9 times 0.9, which is 0.81. Okay. And what about this? So this is going to be the reverse. Now we're going to go in the downward direction. 0.9 times, what's the reward over here? Simply negative 0.1 plus 0 for right now, because there's no further reward. There are no further Q values over here. Plus 0.1 times going in the opposite direction to S4, which would be, what's the reward over there? Plus 1 minus 0.1, so 0.9. So this is going to be 0.9 times so it's going to be negative 0.81 plus 0.09. Let me just double check and see if I'm doing it right. Yeah, it seems to be right. 0.9 times 0.9. Okay. What about this one? So let's do this quickly. Now you're going from state S2 and you're going the upward direction. So it's going to be 90% chances of going in the upward direction. What's the reward over there? Negative 0.1, right? Plus the maximum value of the Q state, given that you take the optimal decision. What is this going to be? Is it going to be this value over here? Or is it going to be this value here? So it should be 0.81, right? Plus 0.1 of going in the opposite direction. And what's the reward over there? Well, the reward over there is, there a question over here? Okay. So the reward over here is negative 1.1, right? Because there's a negative 1 over here reward, and there's a movement cost as well. Okay. So you can calculate all of these. And I'm not going to go through all of these details because we've already done this. Let's just look at how this is solved. So, yeah. So in the second iteration over here, so let's look at this. Everybody's okay with this? It's 0.9 times 0.9, 0.81 minus a little bit of a negative reward going in the opposite direction. And then over here, it comes out to be 0. This comes out to be 0.62. This comes out to be negative 0.92. Is this okay? Where did we make a mistake? In the previous one? It's is the second one over here. So it's plus 0.1. It should be plus 0.1 times 0.9. Oh, sorry. Okay, if there's some mistakes, correct it out. But you know, you've got the general idea, right? I might have made a mistake somewhere. But the point here is that iteratively, you know, this was, somebody pointed out last time that this is not going to be 0.8 as it was in the earlier example. Okay, earlier it was 0.9 and here it was 0.8. So you notice that there are some small differences. It's coming out to be slightly less than 0.9 over here. Why? Because there's a 10% chance of going in the opposite direction. And this is coming out to be 0.67, slightly less than the earlier one, which is 0.8. Okay, why is it a little less? Because now we're 10% of the chance we're actually going in the opposite direction. So is this does this seem to have converged? 0.8, 0.862, 0.62, 0.67. Clearly it's not converged, right? Because the numbers are still changing. So you may have to take this a lot longer, and it's quite possible that it will never converge. In other words, if you're defining convergence to be that the previous value and the current value are exactly the same, it may not actually happen. As you've seen, for example, in a lot of techniques that we've used in gradient descent, for example, you get closer and closer and closer to the final optimal value, but you actually never get to it. In other words, they're not identical. So if you want to be able to converge, you have to decide what is the level of error that you're willing to accept before you just stop. Okay, so you might decide, well, the level of error could be 10 to the minus 3 or 10 to the minus 5 or 10 to the power minus 10, and at some point you will decide, well, the error, the difference between the two is so small that it's pointless keep on iterating. So that's how you will get to a close to the optimal value. So this was Q values under uncertain outcome. Let's take a look at one more case, and this is also important. Now, Q values with discounted future values. So the simplest case was this, and now we've removed the uncertainty. And now the question is, how would you modify this if future rewards were to be discounted? In other words, we all know that a future reward is not necessarily the same thing as the current reward, right? Would you rather get $100 or 100 rupees today, or a year down the road? So as you know, there is inflation, and there is all of that going on. So the value, for example, of money actually reduces. Okay. Similarly, for most rewards, the value reduces as it goes further and further into the future. So the question is, how would you modify this equation to take into account the fact that future values need to be discounted? They're not as useful as the value of the reward today. Okay. So how would you change this equation? Any thoughts on that? So basically what you're saying is that the new value of Q is based on the current reward plus the maximum value of a future reward, right? QST, this is actually the maximum value of the future reward. So which one of these terms would you actually want to reduce? Is it the current value or the future value? Clearly the future value, right? So let's say that you want to reduce this by 10%. Okay, so what would you do? You'd multiply this by 0.9, right? So what we can do is we can change this equation and have what is referred to as a discount factor. Okay, so this is exactly what you were thinking. We're adding a discount factor, and this could be, for example, some value between 0 and 1. And if you want to discount it by 10%, you would make this 0.9. You'd make gamma is equal to 0.9. If you want to discount it by, let's say, 30%, you want to make gamma is equal to 0.7, and so on. Okay, you get the idea. And if you notice that subsequent values, so if you're reducing it by 10%, then something which is 2 time steps further down will actually be reduced by how much? Will it now be 0.9 of the original value, or will it be 0.8 of the original value, or what? It won't be exactly 0.8. And if you've done a little bit of finance, know that you multiply these values. Okay, so it'll be slightly less than that. Okay, so it won't be 0.8, it'll be 0.9 times 0.9. Okay, so anyway, you can solve this out, but it'll be a product of the gamma values. So this was the second type of Q. So we've looked at 2 types of, we've looked at the basic equation, then we looked at the uncertain equation, and we've looked at the future discounted versions. Okay, now I'm not going to combine all of these, but you can combine all of these. Okay, so if I say that, what if you had discounted future values plus you had uncertainty, you can imagine what we would do. What would we do? How would we change this equation if I said there's uncertainty as well? We'd have an expected value, right? So we'd simply put an expected value before this entire thing. Okay. Now gamma is going to be fixed, but the other values will have a probability associated with it. Okay. So that's how basically you calculate Q values. And the last topic in the MDP area is something referred to as exploration versus exploitation. Okay, now what do I mean by that? Now remember when we started talking about, for example, grid world, we said that we will go in a particular direction and we will calculate all the Q values. Okay, so essentially in this simple example, we're calculating the Q values in the upward direction and in the downward direction, right? And until we've actually calculated all the Q values, we can't really go forward. Now think about something, as I said last time, I think I sort of touched upon it. What happens if you have a very large number of possible actions that you could take? Okay, imagine that as you know, a couple of the favorite examples. If you're going from home to IBA, then you don't have just 2 possible ways. You could have, you know, 100 possible ways. Okay. Similarly, if you're playing chess or any other game, you could have a large number of ways to take the next action. Okay. In chess, for example, you have dozens and dozens of different actions that you could take. So if you're doing your Q values, what does that mean? How would this table change? So let's say you're playing chess. How many possible directions would you have now? So if let's say that you have 100 possible directions that you could, 100 possible actions that you could take, then how many Q values would you have to take? You have to take 100 Q values, right? For each one of the possible actions. Now that could be very computationally complex, okay? And so, and if you keep on doing this over and over again, imagine that this table is taking forever to converge, and you're doing all of that computation. That could be very computationally complex. Okay, so in order to reduce the computation, you have a technique called exploration versus exploitation. Okay, what that means is initially, let's say this is a slightly different example. Here's a lizard. Again, this is a grid world, but now the only difference here is that, well, you do have those black boxes where you end up with, you know, a negative reward, which means that you get eaten up by a bird in this case. But what do you notice over here? These are crickets, and lizards love crickets. So you have 2 squares where you have rewards, but are they the same? In one box, you have 1 reward, and the other you have 4, 1, 2, 3, 4, 5 rewards, right? So the rewards are not equal. In the earlier example where I had shown you, the rewards were very simple. They were just +1 over here and a -1. Okay, so the -1 is sort of like, you know, the bird eating the lizard, and the +1 is equal to the cricket getting a reward of the lizard getting a reward of a cricket. But here you can actually have a reward of +5 as well. Okay, why? Because you can actually go somewhere and you can get a whole bunch of rewards. Okay. So the question is, what should the lizard do? So if the lizard was following the normal Q values, approach, it would take different directions. It would go in different directions, and for each direction, it would figure out what the Q values are, and it would do it iteratively. Okay. Now imagine that the number of possible directions, in this case is fairly simple. It's just 2 directions, right? 2 or 3 directions. You can go in the north direction, or you can go into east, or maybe the west and south and so on, maybe 4 or 5 different directions. But imagine again that this was chess and you had 100 possible different directions. So the question becomes that should we always try out all the directions, or should we have a certain approach of initially exploring all the directions and then reducing the number of directions, or do you initially want to start with a few directions and later on explore more directions? Yes. Right, right. So, but the thing here is that if you look at this example, when the lizard is initially exploring the world, it doesn't really know that, suppose that it got to the first lizard, right? It got over here. Now it might say, this is great. I found the reward and I'm just going to keep on going in this direction, right? It's found the optimal solution. But what he is not realizing is that there is another optimal solution which is far better. Okay. So, so if the lizard didn't explore the world, then and what we call as exploitation. Exploitation means that whatever you found so far, you're just going to keep on using that. Okay. And exploration means that, hold on, I know that this path is giving me some nice rewards, but let's be, adventurous and let's explore the world. Let's go into unknown territory. Maybe there's something on the other, on the other side of the hill, which is great, which I don't really know. So you understand the trade-off between exploration versus exploitation. Exploitation is somebody who is very, who doesn't want to be so adventurous, all right, and simply goes and reaps the past rewards. And exploration is somebody who says, okay, I've got some rewards, but I'm going to be adventurous even though I'm not going to get some good rewards, because going in this direction, the lizard is not going to get some immediate rewards, but he is being adventurous. And as a result of that adventure or that exploration, it's going to end up with something which is going to be far more lucrative. Okay. So, so the first question is, when you initially start off your game, so let's say you're going in time. Okay, this is time. Initially, do you want to be, you don't know the world at all. You have no idea that you're going to get, what rewards you're going to get in this direction versus what rewards you're going to get in this direction. Would you want to be, do you want to be adventurous, or do you want to simply be exploitative? Do you want to explore the world, or do you want to simply exploit the world? You want to explore the world, right? Because you don't even know the world. So obviously, initially, you're going to start off by exploring the world. So what we're going to refer to this as something called epsilon greedy, okay? So epsilon is the term, it's the proportion of time that exploration will be chosen over exploitation. So as you said, initially we want to explore the world, okay? So epsilon is going to be initially set to 1. In 100% of the time, you're going to explore. So we're going to start off over here. Now, as we get more and more familiar with the world, okay, do you still want to be as explorative? No, you want to probably, you say, okay, I want to reduce the amount of calculations. So I'm going to try to be, I'm going to be more exploitative. In other words, I'm going to make use of the past results that I have, and I'm going to change this epsilon, okay? So you may want to go in this direction. So you're slowly reducing the amount of calculations that you're doing and exploring less and less of the world. You've simply found a good direction. Maybe you found this path after you've explored it, and you say, well, this is fine. +5 is good enough for me. I don't want to go, in all the other direction, and maybe there's a +50 over here, but, I'm not going to be so greedy. So, sorry? Why would you want to go over here? Why would you ever want to? So why would you ever want to stop exploring? That's a good question. Why don't you be adventurous for the rest of your life? Yes, so that's the whole thing. So let's say you've explored enough of the world. I mean, you've come to IBA 20 times already. You've figured out that, this is the best way. I'm not going to try out some new ways to go through, go through the beach. And I know that it's probably not going to get. So you have enough experience, and now you want to use that experience to be able to reduce the amount of complexity. Okay. So at some point, people become mature, become adults, and say, okay, enough exploration. Okay. So that's the whole idea. It's just reducing computation time. Okay. But suppose that at some point your environment changes. Okay. All of a sudden there's an earthquake, right? And all the streets are now damaged. So now do you want to still go on the usual path that you used to come to IBA? No, now you want to again go into the exploration mode. Okay. Now you're going to try to go through the beach as well. Maybe that gives you a better route. All the known routes are already damaged. Okay. So then what are you going to do? How is epsilon going to change? Epsilon is going to perhaps go back to 1. Okay. So it may not go back all the way up to 1, but if there's a small change, you might increase it a little bit. Okay. And you make it, from maybe 0.5, you may go to 0.7 and so on, but this is sort of a strategy. And this is called an epsilon greedy strategy, okay? So generally speaking, you want to start off with epsilon being 1, you slowly reduce it, and then if something changes in the environment, you want to increase and you want to now start exploring again, and then again slowly you'll start to reduce the epsilon value, okay? So this brings us to the end of the previous topic where we spoke about Markov decision processes. And now we're going to start the next major topic of this course, which is machine learning, okay? So now I'm going to do a bit of a recall. And if you see some of these slides, they will have an R at the top. This is just to remind you what we studied in the very first lecture. We spoke about supervised learning, unsupervised learning. Remember supervised where you had lots of examples, unsupervised where you didn't really have labeled data. Nobody actually told you what was right, what was wrong, but you sort of had clusters. You try to figure out that these are all images of the same person and these images are of a different person and they seem to be quite different. So now you're learning by patterns, okay? And then we spoke about unsupervised, semi-supervised learning, where it's sort of a combination of the two, okay? And when you look at more specific examples of this, you'll get a better idea of what semi-supervised is. And then there is reinforcement learning. And reinforcement learning is actually what we looked at earlier, okay? If you think about what MDPs were doing, that was an example of reinforcement learning. Well, it had a dynamic environment. It didn't have the learning part, okay? So later on, what we're going to do is combine MDP with learning, and that's going to be reinforcement learning. So this is still something that we will study as we go forward. But let's start by looking at supervised learning. This will be our first topic. And just to remind you, I'm going to start, as I said, by looking at artificial neural networks, all right? And these are similar to deep neural networks, which is deep learning, which is again a subset of machine learning. Machine learning, again, is a subset of AI. So now we're jumping into ML by just looking at ANNs. And later on, we're going to look at things over here as well. Other machine learning topics which are not ANN, okay? But you'll have to wait for that. So again, a few review slides. If you remember, we said that we humans have a wonderful organ called the brain, okay? And we all know that we learn over as we're babies and all the way into adulthood, we're continuously learning. So the idea was that if we have the brain, and it's such an excellent example of something which is continuously learning, why don't we actually use the brain, the model, a simple model of the brain, to be able to see how we can actually have algorithms which can mimic the brain to be able to learn, okay? And so we saw that we looked at neurons, and we said that synapses are the junctions of neurons, and we have there are about 100 billion 10 power 11 neurons in a normal human being, and each one of them is connected to 10,000 other neurons, which means is it densely connected or not densely connected? If it was connected to every other neuron, it would require approximately 10 squared number of synapses or connections, right? Which means that it would have 10 to the power 22 synapses. However, you're only connected to another 10 to the power 4 other neurons. In other words, it's not dense at all, okay? So you can think of it, Einstein used to say he's only using 3% of his brain power, right? So you can imagine where that's coming from. That's sort of saying that there is a lot more that can be done with the brain. You can actually have, if for example, instead of 10 to the power 4 synapses, you had 10 to the power 8 synapses, you could probably have, could probably be a lot smarter, okay? But humans obviously have certain limitations and so on. So this is the average human being today. I don't know what's going to happen 100 years or 1,000 years from today. Maybe we'll have those Star Trek type aliens which have these huge brains. They probably have a lot more synapses. So a synapse, if you look at it, looks something like this. you have this neuron over here, this another neuron. These are connected by what are called axons, okay? And then there's a very complex chemical process that's going on which decides how these two are connected. So if a signal comes down this way, all right, if a signal comes down this way, the what impact it has on the other neuron is determined by the strength of the synapse, okay? And this is where all the magic happens, okay? We don't really understand, neuroscientists don't really understand how this happens. It's very complex. It's a very chemical, there's a lot of chemical reactions and so on. And the strength of this synapse will determine how strong is the signal as it passes through that synapse, okay? So if it's very strong, then the signal will easily pass through it. If it's very weak initially, then the signal might initially pass through it, but after a few days, maybe you'll forget, okay? What that means is, suppose that you learn something today for the quiz on Tuesday, right? And then a week later, you forget. So what probably happened? What that means is that that synapse, those synapses were not very strong. And a week later, those synapses actually dissolved and those, they went away. And those connections are lost. But if you repeatedly come back to it, so if we have quiz every week, maybe, then that synapse will become really strong, okay? And then you will remember by the time the final exams come, okay? So the question is, do you want to have strong synapses or weak ones? So how do you represent? So this is the simplistic version of that earlier diagram. This is each one of the, this is a neuron. So a neuron is from here till here. It has a cell, it has an axon, it has inputs over here, okay? So the inputs, could, for example, could be sound or touch or something, okay? And these could be other axons coming in, and then there's a synapse, okay? And the strength of these synapses determine how easily can the signal pass through this neuron, okay? Then inside the neuron, there's also something which is non-linear, okay? What that means is that if the input is very weak, for example, if the input is 0.2 over here, and let's just forget about let's just take one of these inputs. Let's say we're taking one of these inputs, x1, and we're looking at the output over here, which is y. Let's say this is y. And we're saying, how does y relate to x1? So when x1 is very weak, no signal may actually pass through this axion to the next cell. But at a certain point, when the signal crosses a certain threshold, for example, if you're thinking about voltage, let's say this is 10 microvolts, all right? I'm just guessing. Suppose it's 0 to 10 microvolts. At some point, if that signal becomes strong enough, then all of a sudden, the output is going to jump, okay? So it's a non-linear function. And the output is all of a sudden going to send a strong signal down to the other axion, okay? So it's not linear. In other words, for every x1 and x2, it's not just going to combine them and send that small signal. It's going to say, well, if the signals are strong enough, if they're above a certain level, then only am I going to send the signal down, okay? That's sort of like saying that if you're learning something, then if I have some basic concepts, I'm not going to really learn it. But if I really learn it properly, then the next neuron is going to be told that, okay, I understand this concept, okay? So it's going to be, this output is going to be either 0 or 1. It's going to either send a signal or it's not going to send a signal, okay? Now, how does this relate to an artificial neural network? Now, as I said, the brain is extremely complex. What we're going to do is we're going to make a simplistic version of this model of the brain, okay? And this is the first version of this includes only a single cell. So this, a single cell is going to be replaced by a single perceptron, okay? A perceptron is simply a model of a single cell, all right? Now, if you look at it, this is, how does it work? Your inputs are still the same. So x1 and x2 are the same, okay? So if I go over here and I compare it with, let's say this was your, the biological version. So it had x1 and x2, okay? Again, we have x1 and x2 over here. It had an output y, we also have an output Y. All right. Now we've introduced certain things, the weights. Now, why do you think we're introducing these weights? What do you think they represent? Sorry, the synapse. Okay. So if the synapse is strong, what do you think this weight will be? The weight will be higher. Okay. So if W1 is very strong and W2 is, let's say, close to 0.1, and this is, let's say, it's let's say 10, then clearly it implies that, for example, if X1 is sound and X2 is touch, then that means that this signal is going to respond to the sound immediately, but it's not going to respond to touch as quickly because it's not been trained on touch. It's sort of like, when your mom comes in the morning and she shouts at you, wake up, right? So, you now tuned to that sound, but she doesn't move you around. So you're not tuned to this, to the touch. So that's kind of like a real world training. So W1 could be, each one of them could have different values depending on which one of these synapses has been more trained, okay, or is stronger. Now F over here, F and phi together are representing that non-linearity. The first portion, F, is going to be, is this linear or non-linear? Is this equation F is equal to summation of Wi? So I'm taking a weighted sum of the inputs and I'm adding a certain bias as well. Is this equation linear or non-linear? It's linear, right? Clearly it's linear. If I had an xi squared, would that be linear? No, that would not become non-linear. All right, so I'm not going to add that. So this is the F portion. The F function is simply a linear combination of the inputs, and it's a combination based on the weights of each one of them. So it represents the strength of the synapse. And then there's also a bias. Now, why do you think the bias is there? So if you look at this, if you think about this, the bias sort of changes the position over here. At what point does the output actually go forward? Okay. So as you look at some examples, you'll understand what a bias means. Now the phi over here represents the non-linearity. Okay. And I'm going to use a simple example of phi, which is the step function, which basically means that if f is less than or equal to 0, the output is going to be 0. Okay, you can see that over here. And f is greater than 0, it's simply going to be a 1 over here. Okay, so this is called a step function. So, G. Sorry? No, not necessarily. It could depend on how you're trying to shift this. So, for example, if you're trying to shift the step function over here, would B have a positive value or negative value? You think about that, okay? Or if you want to shift this in another direction as well. But we look at examples which will make it clearer. So, so now the combination of F and phi are basically trying to model the non-linearity in the original biological neural network. Okay, so so now let's take a look at this example and try to understand how does this help. Okay, how does this help in learning? And this will become clear as you look at a simple example. So, so let's think of a simple learning example, and we'll refer to this as a classification problem. Okay. So what we're trying to do is we're trying to learn how to classify dogs and cats. Okay, simple example. And we're going to do this based on a collection of given input-output pairs. So this is going to be an example of supervised learning. In other words, somebody's already told us, has given us a bunch of examples of what are cats and what are dogs. Okay. Now, we're going to be given certain features. Okay, these are going to be called features. So for example, you can think of what features differentiate dogs and cats. Can you think of a bunch of features? I've shown you a couple of features over here, but these aren't necessarily the only features. So I've said, let's look at weight and friendliness. Okay. In other words, if weight is very large, Okay, and it's probably a dog, right? Because cats are small. And friendliness, if you can have some measure of friendliness, you could say that dogs are generally more friendly. Okay, but you could have examples of something which is, this is a dog, which is it heavier than a cat? This particular, so we got these label data. So somebody's told us that here's a dog, its friendliness measure is over here, and its weight is over here. All right, here's another dog with this weight, and here's another dog, and so on. And here's a cat, here's another cat, and so on. So they've plotted the cats and dogs on this two-dimensional space. Okay, and as you notice that this dog, if you call this, let's say, cat 1, and this is dog, let's say this is dog 1, this is dog 2, this is dog 3, cat 1, cat 2, and cat 3, you notice that dog 2 actually weighs less than cat 1, but it's more friendly. Okay, so you can see that if you want to differentiate between these two, and you had this plotted for you, how would you, as you know, just by looking at it intuitively, how could you differentiate this? And how would you differentiate this? Sorry? Say that again. You could add more factors. So for example, you could have another factor over here. All right, I could make another dimension. Let's say, what other dimensions could you add? Give me some more examples. Sound. Okay, so you could say the strength of the sound. So the cat would be in terms of decibels, it would be a lot lower. The dog would be a lot stronger. Very good. So there could be other features. We will call these features. Okay, so the sound level when they speak or bark or meow or whatever. What else? What could be other features which distinguishes dogs and cats? Come on, I'm sure a lot of you have pets. Sorry?
Height could be a factor.
Height, did you say?
Yes.
Yes, so it could be height, it could be length, you know, it could be lots of things. It could be color, it could be the shape of the nose, it could be the length of the tail, it could be the length of the hair, and so on. All of these would be considered as features of these two animals. Okay, but for the sake of simplicity, simply because we humans have this ability only to look at two-dimensional graphs, and it becomes very difficult in 3 dimensions. So I'm not going to look at higher dimensions, and I'm only going to look at 2 features. Okay, so suppose that you didn't have a third feature and you only had 2 features. How would you, given this particular set of data, how would you train yourself to be able to differentiate this? So suppose I gave you a new animal, right? I don't know what this is. What would you classify this as?
So we could make a line.
Okay, so you simply draw a line. As you can see that you can draw a line over here, and anything which is on the right side or sort of above this line would be a dog. Anything which is below this line would be a cat. Okay, so this is what is referred to as linearly separable data. Okay, so this is linearly separable. Okay, why is that? Because you can draw a straight line between those points, right? So what if you found something over here which was a dog? Is it possible to have a dog like that? Sorry? It's possible. You know, have you seen those really tiny dogs which people put in their pockets? So it's possible that a dog could be really small, and maybe it's not very friendly either. Okay, so it's quite possible that not all of these animals will fit these linearly separable boundary. Okay, you will have some dogs which are, and you may have some cats over here. Have you seen Garfield, for example? Huge weight, and it's not very friendly, and it's not friendly either. So you can have exceptions to the rule. Okay, so when you have non-linearly separable, the problem becomes a lot harder. Even, for example, for us, for example, if you had these two, how would you differentiate between this new animal? How would you actually start to tackle this problem? You've got a cat over here, you've got a dog over here. All right. So I've got a new animal over here. I want you to be able to figure out whether it's a dog or a cat. This is a classification problem. Okay. And based on the past data, okay, so you've got a bunch of input-output pairs. The input is the features, and the output is the label that it's a cat or a dog. Okay, so based on a bunch of input-output pairs, we're now learning some kind of a function. Okay, so we're learning a function. In the first case, we learned a function which was simply a straight line, and we said that if we can learn this function optimally, then we can figure out whether a new input. Okay, so if you have a new input, okay, for new inputs, we can figure out whether the new input is either a dog or a cat. Yes. Very good. So you could make clusters, right? So what we could do is we could say, well, here is a cluster. All right. Doesn't look very easy to draw. And here's another cluster. Okay. And this cluster is really weird. So it's going like this. Okay. So these are two clusters. Here's one cluster, and here is the other cluster. Okay. Now, unfortunately, in this particular example, these clusters are going all over the place. So if you have a new item, you don't really know whether it's going to be in the first cluster or in the second cluster. Okay. In the first example, where it was linearly separable, it was very easy. But when your data started to overlap in the linear space, then you had problems. Okay. So we'll try to tackle these problems one by one. Okay. So the first problem that we'll try to solve is a linearly separable data. Okay. So we're going to solve the first problem by looking at if we can use the single perceptron to be able to solve this problem. Okay. Now the question is, if you remember the single perceptron equation, it was F. Okay. F. Just forget the F1. F is equal to W1 X1 plus W2 X2 plus B. Okay, we already went over that, and we're going to use phi as a step function. Okay, and I'm going to give you a bunch of inputs. So here are three inputs, and all of these are cats. So input number one, serial number one, is a cat. This is the input-output pair. So its label is X1 is 2 and X2 is 2. Okay, so X1 could be the weight and X2 could be friendliness and so on. Similarly, we've got another cat which is label number 2, and we've got another cat which is label number 3. This is given. All right. Now we've got 3 dogs given as well. So this is the simple case. You can see that it is linearly separable. All right. Now my question is, what values of W1, W2, and B would you choose so that you can draw a line through it? So where should the line be, first of all? The line would be clearly would be somewhere over here, right? Now, can somebody tell me an equation for F which satisfies this line? Going back to your calculus. Y is equal to mx plus c. Remember that equation? This is the slope, and this is the point where it cuts the axis. So just looking at it, can you tell me the equation of this line? Sorry? It has a negative gradient of probably a -1, because you can see it's symmetric, right? So 1, 2, 3, and 4, 5, 6 are symmetric. So probably the gradient should be -1. Okay. And sorry? So, well, I'll just tell you the answer. You can see that X1 plus X2 should be equal to 10, right? So over here, you can see if this is 10 over here and this is 10 over here, this particular line which goes through that has equation X1 plus X2 is equal to 10, right? So, so what are we going to make W1, W2, and B? What should be the equation of this line? I've already given you the solution over here. Just draw it out now over here. So now at this point, the function f has to be equal to what? This line is going to differentiate. It's going to go through a step function, and the step function, remember, is a very simple step function. It is going to, for things which are less than 0, is going to give an output of 0. For things which are less than 1, for greater than 1, is going to give an output of 1. Okay. So it's going through a step function, and we want y to be equal to, for example, zeros over here. In other words, if you want the output to tell us it's a cat, we want y to be a 0, and we want y to be a 1 when the output has to be a dog. Okay. So now I'm trying to make you think, what should be the value of this line if it's the line which is differentiating between these two categories? F should be equal to 0. Exactly right. So the function over here should be 0. In other words, if f is greater than 0, if a value over here, if f is greater than 0, it's going to result in y being equal to 1. And over here, if f is less than 0, the output of y is going to be equal to 0. Y is going to be 0. So that's how we will know that these are dogs or cats. Okay, so we're making progress. So we figured out that this line over here should be equal to 0. Now, if this is equal to 0, can somebody tell me what should the values of W1, W2, and B be now? Yeah, they can be 1. Okay, so they don't necessarily have to be 1, but because we know that the slope is equal to -1, so you can guess that you want to make this 1 and 1 over here. Okay, so we can make W1 as 1 and W2 as 1. And then B should be -10. Exactly right, right? Because you want to make x1 plus x2 plus b equal to 0, so B has to be -10. Okay, so far so good. We've solved this, and F1 clearly is equal to what? So we've solved this. What's y equal to? Y is simply equal to phi of f, which simply means it's the maximum of 0, f. All right, that's another way to show this step equation. In other words, this equation is simply equal to maximum of, that was the ReLU equation. It's simply equal to 0 or 1. Okay, that was wrong. So this is simply equal to the step function. Okay. So we've solved this problem, and now let's try to see if we can get the right values. Can somebody help me fill this table now? So we've got 2 plus 2 minus 10 is equal to what? -6. So this is going to be a 0, right? Because it's less than 0. What is this going to be? 5 plus 2, 7. This is going to be -3. 5 plus 2 minus 3. This is going to be 0 clearly. This is going to be now 10 plus 5. So this is this point over here. It's going to be 15 minus 10, which is going to be plus 5. So this is going to be a 1 over here, right? This is going to be a 5 plus 10 plus 5, again a plus 1 over here. This is going to be a plus 10 over here, again a plus 1. So we can see that we've cracked the problem using a single perceptron. All right, single perceptron is able to classify any set of data which is linearly separable. Okay, so far so good. Now let's take a look at a slightly more complex problem. So this is the problem that I showed you earlier, which is now that you have some dogs which are over here. All right, this could be more and more complex, but let's look at this particular example that you have this scenario. And now if you were, as a human being, trying to differentiate between these dogs and these cats and these dogs, what you could do is perhaps draw two lines, right? So you could draw a line over here and you could draw a line over here. Okay, would this be considered as a linearly separable problem? Actually, no. It seems like it's yes, but because you can draw two lines, but actually this is, if it's only linearly separable if you can draw one line in 2 dimensions. If it's 3 dimensions, you should be able to draw a plane through it, and so on. Okay, so you can't draw multiple lines. That will be considered as a non-linearly separable. So this is non-linearly separable. Okay, another question is, can the single perceptron solve this problem? Okay, so if this is linearly separable, this is not linearly separable. Okay, so And this can be considered as a class of problems. In a simplistic way, this can be thought of as an XOR problem. Okay. All of you most of you studied intro to computing with me, right? So I'm sure you remember what XOR is. The XOR function goes like this, right? X1, X2, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. You thought this would never come in handy again, but here it's coming in handy in the fourth semester. Okay, so the XOR function. Now, why do you think this XOR and this function are sort of related? Can you see a resemblance between this problem and the XOR problem? Why? Because you can see that if you look at this, as x1 is becoming larger, for small values over here, you have one set of values. Over here, you have the same set of values. And in these two quadrants, this quadrant over here and this quadrant over here, you have different values. So you can see that this XOR is sort of similar to this. Okay, and you can draw two lines through this, and then it can be sort of linearly separable with two lines, but that's not linearly separable. But you can see the resemblance between this problem, which is more general, and let's convert it into a simpler problem in which you just have 4 data points. Okay, you have examples of let's say 1 dog, 2 dogs, and 2 cats. Okay, 4 data sets. So first, what we'll try to see is if we can solve this particular problem, the XOR problem. If we can solve this, then we can solve this. Okay, that should be clear. So what we'll try to do is see if we can solve the XOR problem using, well, we could try using the single perceptron. Okay, and if we can't do it with a single perceptron, then we can try something more complex. Okay, so the first question is, do you think we can solve it using the single perceptron? So remember, F is a linear equation, okay, and phi is a non-linear. So phi can be, we can change phi as well, okay. Phi can be, for example, a step function. It can also be something called a ReLU function, okay. It can also be something which is called a sigmoid, which we'll talk about later, okay, things like that. So if you're using a linear function over here, and we're using a single step function, do you think this problem, the XOR problem, can be solved using a single perceptron? No. Why do you think not? Yeah, so basically one of the limit, you're right. Your intuition is absolutely right. We can't solve it. One of the things that should give you a hint is that the F function is a linear function, okay, and that sort of indicates that you can have one line, but you can have multiple lines, okay, and that sigmoid, that non-linear function, is basically being used to differentiate whether you're on which side of the line you are, okay. So the single perceptron problem will not be able to solve this, okay. Now, how can you? So let's say that I can make this into a neural network. If you think about, go back to your neural network, right? This was your neural network. Now, this over here, I showed you not just one neuron, but I showed you another neuron connected over here. I showed you another neuron connected over here. And that's why it's called a network, okay? So you could have multiple perceptrons connected to each other. You could have one of these feed into another one. You could have 2 of these feed into a third one, and so on. And each one of them has some non-linearity built in over here. So the cell inside has a non-linearity in it, okay? So can you think of a way to be able to combine this into into a bunch of perceptrons which could perhaps solve this problem? Okay, so let's show this as a single perceptron. Okay, this entire thing I'm going to show as a single perceptron. And I said that you can combine these. How would you combine these? I could say that the x1, now there are only 2 features, right? So you have x1 over here and you have x2 over here, right? So how can we combine more perceptrons so that we form a network? Now the output doesn't necessarily have to be the output of the first perceptron, right? So can you think of ways to combine these perceptrons? We could have another one over here. Sorry? We could change the weights, but changing the weights is not changing the perceptron. Remember I said the weights could be anything. So a single perceptron can have any arbitrary value of weight, and it can have any arbitrary value of the bias. That depends on the training. Okay, so as you give it more and more data, hopefully we haven't figured out how to do the training yet. All we've done is we've been able to intuitively figure out that this equation over here can solve this problem. Okay, and we did intuition. We haven't actually figured out how the real learning is happening. All right. So by intuition, we figured out that we could make these values W1 and W2 equal to 1 and the bias equal to -10, and we were able to solve a very simple problem. Okay. So by changing the weights, we're not changing we still have a single perceptron to solve the problem. Okay. Now what I'm saying is a single perceptron can't solve this problem. And I'm saying throw in more perceptrons, make a network out of it. All right, make a network out of it and see whether you can solve this problem by having a bunch of perceptrons. Okay, so how would you add it? So you could, for example, add another perceptron over here. Okay, this output of the first perceptron could go into the second one. Okay, you could add a third perceptron over here and so on. You could have a chain of these. How else could you form this network? So this is one way to form a serial link, right? Can you think of other ways of combining these perceptrons? So this is serial. What about parallel? Can you form a parallel network? So what I could do is add another perceptron over here. And then what would be the inputs? Same and X1 and X2, right? Exactly. So we could add the same inputs to both of these perceptrons. Okay, but each one of them would have their own weights. So the weights over here would be different. For all of these weights could now be different. The bias for each one of these could be different over here as well. Okay, and so on. So you could make it very complex. You could keep on making this more and more complex. All right, and you could add more perceptrons at the bottom as well. Right, so you could add another perceptron over here, and so on. Okay, so this is how you actually form a neural network. And the deeper that so this is the output over here, final output. So the deeper that you go over here, that is called a deep neural network. Initially, people didn't think of that. And they just thought of a single neural network, right? They used to add things in parallel. But then later on, they realized that going deep also made a difference, okay? So here's a simple, what is referred to as a multi-layer perceptron. And what we've done is we've combined 3 of these together, just like we did earlier. So now we've got perceptron number 1 over here, perceptron number 2 over here. These 2 are in parallel. And this one is a series, okay? And you could now think of the kinds of equations that would combine these. So you could have a different weight for each one of these. Now I'm saying W11 is the input from 1 to 1. 1 to 2 is the input from X1 to the second perceptron, and so on. Okay, you could come up with the different weights. The bias over here could also be different. So this is bias 1, bias 2. Okay, and the outputs, let's say we're calling these the outputs. The outputs could be combined with different weights with a third bias to combine that to a subsequent perceptron. Okay, and you could again form a very complex network of these as you wish. Okay, so we'll come back to this and we'll take a look at this. So you can imagine what the equation over here is, right? So I hope I don't have to explicitly tell you, but think about this. Think of this equation and these equations. But before I generalize this, let's take a look at a very simple example and see whether it actually solves our problem. Okay, so here's a 3 perceptron problem. Okay, and I found a solution to supposedly a solution to this XOR problem. Okay, this is the XOR problem. Remember that you have these ones over here and you have these zeros over here. Okay, and my claim is that this particular 3 perceptron solves this problem. Okay, how did I get this? I actually saw it in one of the books. Okay, it's a book by one of the leading gurus in this field who actually did a lot of research in this area in deep learning. When you could take the course in deep learning, you'll probably refer to his book. So, so now I'm using these specific weights, and now let's try to see if we can use this example over here, and to see if in fact you can actually solve this problem. Okay. So, what's the first equation? F1 is equal to what? So the weight over here is 1, and the weight over here is 1, and the bias is 0. So what's the equation for F1? X1 plus X2 plus 0. Okay. And F2 would be equal to X1 plus X2 minus 1. Right? Very good. What's Y1 equal to? Now, this is a different equation. It's a max equation. Okay. This is what is referred to as a ReLU equation. I think I showed this to you earlier. Yeah. So you can have, as I said, different types of nonlinearities. This is a very common nonlinear equation which is used. Okay. This looks like this. It's maximum of 0, f. So if f is less than 0, it's equal to 0. Right? If f is greater than 0, it's not equal to 1, as in the step function, but it's equal to f. Okay. So as you can see, this equation simply goes like this and goes straight up. Okay. So this is referred to as a ReLU or rectified linear unit. It's a mouthful, but it has linear in it, so you can imagine. And it's coming in from, I think, electrical engineering. That's why it's called a rectified linear unit. Okay. So we'll just call it a ReLU equation. So let's go on. So what would Y1 be equal to? Now I'm already telling you that it's the ReLU equation. So can you just tell me what the equation is? Maximum of 0, F1, right? Because this is the output of this here, and it's taking the maximum of 0, F1. What's Y2 equal to? Maximum of 0, F2. So far, so good. What's G equal to? Now, G is simply the same thing repeated. Okay. Now, it's taking the output, these two early outputs, and it's doing a linear combination of these two. It's multiplying it by these two weights. So what should G be equal to? Y1 minus 2y2 plus 0. Very good. So you got the idea, right? What should Z equal to? Now Z again is using the same nonlinear equation. So what? Sorry? Max of 0, G, right? So it's simply the same thing repeated. So now you can see that you can write all of these equations if you're given a particular network with certain weights and certain non-linearities in it, then you can actually write down these equations. These are, by the way, called forward equations. Okay, forward equations. We'll come back to backward equations subsequently. So once you have this, in the next lecture, what we'll simply try to see is we'll try to fill this matrix and see if it actually solves the problem or not.